On to section 4.5, where we'll look at gravitational force and weight. Here the objectives are to describe the connections between force, mass, and weight, and be able to use a weight equation to create free body diagrams, and from there be able to solve some problems. To begin, let's start with the question, what direction does the force exerted by gravity act? Now, your initial reaction might be to say that, well, the force acts downward. To really be exact, though, it might be better to say that the force of gravity always acts towards the center of the Earth. So wherever you are on that Earth, gravity is always going to pull you inwards towards the center. Now, the magnitude of this force is called weight. And since weight is actually a force, we can relate it to F equals ma. And in finding this weight force, all we would need to know is the mass of the object and its acceleration. So what is the acceleration of an object that is acted on by gravity? Acceleration simply or solely by gravity is of course going to be your 9.8 meters per second squared. We usually will call that lowercase g in an equation. So since F equals ma, weight is that force, and we simply need to know the mass and the gravity, we come up with this simple equation for finding weight. Usually we'll label weight on a free body diagram or in a force problem as F sub g, since it is the force created by gravity, and you can find that by taking the mass multiplied by g in that location. If you're near the surface of Earth, that g can be plugged in as 9.8 meters per second squared. Remember the difference between mass and weight. Make sure you understand that. Mass is an inherent quantity to an object, simply based on the number of atoms that you're composed of and what types of atoms those are. That quantity would be the same no matter where you go, whether you're in deep space, on the surface of Earth, on Jupiter, or on the moon. Weight, on the other hand, you can clearly see is going to be dependent on location because it's dependent on that value of g. Mass might stay the same, but you could be multiplying that mass by 9.8 if you're on Earth, by 1.6 if you're on the moon, or by something over 25 meters per second squared if you were on Jupiter. That's going to change your weight by changing the force that gravity in that location is pulling down on you with. So, how could you change your weight on Earth without any sort of diet or exercise? The answer is change your location. Depending on where you are on the surface of Earth, could slightly change that value of A or G. If you're at the very peak of Mount Everest, you're going to be farther away from the surface or the center of Earth, and gravity is going to be a little bit less. If G is smaller, your weight is now smaller and you weigh less. If you're going to be down by the Dead Sea, you're going to be closer to the center of Earth, have a stronger pull from that acceleration due to gravity, G is going to be larger, and you're going to weigh more in that location. So let's say that you have a 70 kilogram object or person, and they're in a location where g is equal to 9.8. If we wanted to find their weight, F sub g would simply be equal to their mass of 70 multiplied by that acceleration of 9.8 meters per second squared. In this case, if you want to pull out your calculators and solve for that, you'd find that your weight in this location is about 686 newtons. This is a very typical value for an average size person. So somewhere around 70 kilograms, somewhere around maybe 700 newtons, that could be very typical for a person. Get used to those values so that you understand what would make sense in a problem and what values would be very unreasonable, and you'd maybe check your answers. Now, what if we changed the value of g? Instead of being 9.8, what if it was something a little bit less? In this case, we'd simply change that value in our equation. Rather than 9.8, we could plug in 9.76, and we could see that this person's weight is now going to change, and they're going to be slightly lighter in this location as 683 newtons. So clearly you can change your weight by simply changing your location by changing that pull of gravity. Notice that although weight and mass are not the same thing, they're definitely closely related. In fact, if you were looking at a given location, the ratio of masses of an object would be equal to the ratio of those weights in the exact same location. So you could take a heavy thing and a light thing, the ratio of masses would be equal to the ratio of weights. Does that object necessarily have to be moving for that weight equation to apply? if the weight is equal to mg, does the object have to be in free fall? Obviously, the answer is no. You don't have to be in free fall in order to have weight to you. So just standing on the surface of Earth, you can simply plug in that 9.8 meters per second squared for gravity and know what your weight is going to be. The mass in this equation is really just being interpreted differently from the mass in other force equations. In other equations, it was that resistance to a change in motion or response to an outside force. Here, mass is going to determine that strength of that gravitational attraction between the Earth and the object. So we call mass in this case a gravitational mass as opposed to an inertial mass. Let's create an example where you're looking at now beginning a free body diagram of yourself and labeling the forces. Again, the point of understanding that weight equation is so that when you have a situation or a scenario, a problem that you're trying to solve, you're able to create an accurate free body diagram. So let's just maybe create a diagram for a person who's maybe 150 pounds. Again, we'll look at some average numbers here to compare pounds to kilograms to newtons and be able to see all those things. When converting pounds to kilograms, there are 2.2 kilograms in every pound. So if I set up a conversion factor down here, 150 pounds, and multiply that by the conversion factor of 2.2 pounds in every 1 kilogram, you can see that I would essentially end up dividing my 150 pounds by 2.2. When you do that, you get around 68 kilograms. So this is a 68 kilogram person. If I wanted to diagram the forces that were acting on my 68 kilogram person, I would see that this person obviously has weight pulling down on them. And if they were standing on some sort of a surface or a floor, they would also have to have a normal force pushing them up. So gravity is trying to pull them down. A normal force from the floor is holding them up. We could label the values of these forces by again realizing that the Fg value is simply going to be the mass of this person, which we found to be 68 kilograms, multiplied by gravity in that location. Again, if they're on the surface of Earth, that would be about 9.8 meters per second squared. When we multiply that out, again, pull out your calculators, you get about 668 newtons. So if I were labeling this force diagram, F sub g is one of the forces acting on the object or the person, which would be 668 newtons. And if this person was not accelerating upwards or downwards, their normal force would also have to be equal to 668 newtons. Basically, the floor is going to have to push up with just as much force that's pulling down in order to support the person.